Okay, I want to continue our discussion of Chapter 10 on network protocols. If you recall last time, we talked about the basics of the TCP/IP model, how in order for data to be transferred over the internet, the source and destination nodes, typically computers, they might be a mobile device, have IP addresses assigned to them. And then so each packet that's sent out has the destination IP address in it. And then routers are responsible for making sure that the packet gets to the final destination network and ultimately to the destination node. Included in the packet is the source IP address so that the destination computer can format a reply to that original source address. Um, Today I want to talk a little bit about TCP over wireless. Now this is not Wi-Fi, this is TCP over the cellular network and some of the special demands for TCP over cellular. I'm not going to go into the details here, actually kind of understanding some of this information requires more in-depth knowledge of the TCP protocol and how it works than we went into it. And it's not even provided in the textbook, for example. And then I'm going to talk about the next version of the Internet Protocol, IP version 6, why there's a need for it. So providing a solution for networking, TCP/IP networking, and over the cell phone environment. Again, network layering provides a good abstraction for the different layers of the network model. With wireless networking, we're typically limited by interference as opposed to with wired networking. Often the limiting factor on throughput is actually congestion. So information delivery capability depends on the channel quality, the number of interferers, the signal noise ratio. So typically sending IP packets over a cellular network requires some adaptation in the physical and link layers to make more efficient usage of resources. Changes also need to be made in the mobile stations and corresponding base stations to ensure compatibility. So with a typical wired network, at the top, the data is sent from the source to destination along a number of different routers. And then the TCP packets are actually acknowledged individually. And then so if an acknowledgement isn't received by the source, the data is resent. Again, this is with TCP networking, and this is all hidden from the application programmer. This is taken care of automatically by just choosing to use TCP. It's built into the network model. The alternative transport protocol is UDP, where packets are not acknowledged. They're just sent across. They may or may not actually arrive at the destination. The source doesn't know, but UDP again is more suitable for streaming services. For a wireless network, there are a couple different approaches in order to adapt the internet protocols to use over the cellular network. One of the big issues here is that there's a backbone network that's used for communication between base stations, and that can use the standard, and typically does use the standard TCP/IP protocols of the network. But for connections between the base station and the mobile station, and this could be two mobile stations communicating. It could be a computer to mobile station, or mobile station to computer. But the link between base station and mobile station typically has to be adapted for use by the internet protocols. There's a couple different ways to do that. Some require modification of the TCP protocol at both the source and destination. Of course, that's a little bit more difficult. Ideally, we would be able to um, um, bring mobile stations and add the cellular network into the internet without requiring any modification to existing devices that are on the internet. Um, Most of the applications that are used, a lot of the applications require use of the reliable transmission layer, or TCP. Of course, that's certainly true for file transfer. Web browsing falls into that category as well. Things that do not are streaming video and streaming audio. So we'd like to, bring in our wireless network so it supports existing applications transparently. Like being able to browse the web or watch video or audio from your phone versus from a computer. There was some limitations of the wired version of TCP for use with mobile stations. The routing information protocol that's used to determine the route between source and destination nodes wasn't really designed with mobility of nodes in mind. It was designed assuming that the nodes are fixed. And packet loss can occur because of random errors as well as due to congestion in the wired network. And then there can be decreased efficiency due to TCP's congestion avoidance mechanism. What happens with TCP, there's a mechanism by which a data window can be reduced in size so that the packets become smaller and smaller in the hopes that congestion will be avoided. And that's not typically a problem with mobile networks where we've got a fixed data rate and a fixed data channel, depending on the number of frequency division multiplex channels or time division multiplex channels or code division multiplex channels we may have. Again, the TCP/IP protocol was not really designed with mobility in mind. So there have been a couple of modifications proposed to either the TCP protocol or the underlying data link layers. And I'm not going to look at these too much. Some of them actually do require, like TCP SAC requires that the TCP software on both nodes, both source and destination nodes, be modified to support TCP SAC. So it's more efficient because regular TCP requires acknowledgement of each packet. TCP SAC selectively acknowledges certain packets. With the WTCP protocol, actually doesn't require any modification to nodes on the traditional internet. It separates the flow into wired and wireless segments, and then uses local retransmission along the wireless segment for any packets that need to be retransmitted. So it's kind of almost like you've got two network links, two internet network links, one between a traditional node on the network and the base station, and then a second node between the base station and the mobile station. And then Freeze TCP protocol will detect impending handoff where connection may be lost, and then will advertise back to the source a 0 window size, forcing the sender to send smaller and smaller packets, and then hopefully maintain the connection over the handoff in that case. A couple others: explicit band state notification. Again, local retransmission from base station to the mobile station. Fast retransmission tries to reduce the effect of the mobile station handoff. Again, that can be a problem because the traditional internet wasn't designed for mobility in mind, where we may have to make and break a connection. Okay. and then actually at the link layer, at the lower layers, there have been some various protocols that have been proposed for use for mobile stations. These will take place between the base station and the mobile station, and so don't require any modification of the TCP/IP stack that's used at the node that's on the traditional internet. And so I'm not going to go into any detail on these. Um, Again, some other solutions that require breaking the connection down into two segments, one into the wired and one into the wireless, have actually been proposed, called indirect TCP and MTCP for Mobile Transport Control Protocol. Okay. I talked a little bit about IP version 4 last time. So let's see, I guess the IP version 4 is probably 40 years old now. So remember, it was designed using 32-bit addresses for every computer on the internet, and originally it was intended that every computer or device that was connected to the internet would be able to communicate directly with every other device on the internet. Well, with 32 bits, there are 2 to the 32 different possible source addresses. That's a little over 4 billion addresses. At the time of development of IP version 4, it was never imagined that we could have more than 4 billion nodes on the internet, each node requiring its own address. Well, now we're well past that 4 billion limit when you take into account not only all the computers, but the desktop computers, laptop computers, pad computers, and then now mobile devices. And then we're getting things like you can, with the Internet of Things, you can connect every conceivable device to the internet. So we're well past that 4 billion limit. So there have been so there have been a couple of fixes to that proposed. The long-term solution is to move to IP version 6, which uses a 128-bit address. And it's my understanding that that's large enough to give every atom in the known universe its own IP address. So that should certainly be sufficient for us as we go forward. In the meantime, a couple of other solutions that have been used is one that's known as network address translation, and that's commonly used where a local area network is separated from from the internet by a router that also serves as a network address translation device, so that all of the computers on the local network can't be reached from outside. And this is typical of UE's network as well as most home networks. You can't, from outside the university, directly reach a computer in one of our labs, for example. You can go the other way. You can go from one of the lab computers to a server out on the internet, and that communication will take place just fine with network address translation. But you can't go from outside the university to one of the lab computers. All of the traffic coming out of the university from the lab computer appears like it's coming from one IP address. I think actually the university has a couple of different IP addresses. So there's some websites. Just Google, what's my IP, and pull up the corresponding page, and then you'll see what the internet thinks your IP address based on the network address translation device that you're using. And that won't actually match the IP address that's assigned to your local computer. Actually, I pulled, so if you remember on my local computer last time, it has an IP address of 192.168.1.3. That's actually what's known as one of the unroutable IP addresses. Let's see if I can, yeah. Here's a corresponding Wikipedia page on private networks. And so you see that any of the addresses in this 192.168 range are used for private addresses. There aren't route tables across the internet to route traffic within this address range. So again, all of the computers on my local network can communicate with each other using this 192.168, but there are a couple limitations. I can't directly reach my my desktop computer, this computer, from outside of my local network. So you know, I'm at home now using this device, but I can't set up a server, you know, a web server on this particular computer and reach it easily from the outside. I say reach it easily because there are always, you know, workarounds to these different problems. So you can set up servers on internal networks, but you know it's you know, it's not easy to do that. Now again, I can get outside to any public servers. You know, UE has a couple of servers on the internet, not many, you know, fewer than 10, that have IP addresses that can be reached from anywhere in the world. CS Server is one device that one computer that we have that we can actually reach from anywhere on the world because it has a routable IP address. I think inside the university they use a 10 dot IP address range, and this is an unroutable IP address range, all of the 10 dot numbers. And you'll see these often used for larger networks. The 192.168 splits the 32-bit IP address up into a 16-bit network part and a 16-bit host identifier. So with 16 bits, what is that? You can have 64,000 computers on the local network. The 10 dot addresses split it up into an 8-bit network part and then a 24-bit host part. So with 2 to the 24th bits, you can have, you know, an incredible number of, I don't know, whatever that is, 2 to the 24th devices on U of E's network. Now again, UE and certainly UE is not going to be the only 10 dot network. There are a lot of 10 dot networks used by universities around the world. But again, most of their traffic appears to be coming, as far as the external internet is concerned, from a valid routable IP address. Let me actually, so, you know, my IP address here is 192.168.0.0. You know, if I go to what is my IP, there are several different services. Actually, what I get directly from Google is my IP version 6 address. Let's try this, whatismyip.com. And it shows my IP address as actually being coming from 174.241.1.108 when I know my computer IP address is actually 192.168.1.3. And it does does identify my internet service provider wireless. That is correct, but it shows all the traffic is coming from Lawrence, Indiana. I'm not even sure where Lawrence, Indiana is. But again, this is not my actual IP address, but as far as the rest of the internet is concerned, it appears that the traffic is coming from this particular IP address. Now, if I want to set up my own web server in my home, what you can typically do is contact your internet service provider and get assigned a routable IP address, one that is visible to others on the internet. So that's one solution, but that's going to cost you more money to do that, actually. So there are other workarounds that are possible if you want to set up a server on your home network. So network address translation was one of, has actually extended IP version 4 well beyond its expected lifetime, that if every computer had to have a unique IP address. Again, this 10 dot network and the 192 network are used over and over by personal networks and university networks around the world. So we have a lot more than 4 billion devices available. But the IP version 6 is proposed as a solution. It uses 128-bit source addresses, source and destination. The header is actually a little simpler than IP version 4, so it actually makes it a little faster to route. Designed to address the unforeseen growth of the internet and the limited address space provided by IP version 4. So 128 bits long. It actually has a flow label, so you can prioritize packets. Has options, and the base header are separated, making it's a simplified header. It actually makes routing faster. And then IP version 6 has support for encryption and authentication built into the IP layer. With IP version 4, that's built into a higher level, the transport control protocol level. Okay, so this gives some of the information about the different fields in the header. Okay. So as we transition from IP version 4 to IP version 6, most computers now in this transition phase have both stacks installed. And as you saw earlier, my computer actually does have both an IP version 4 and an IP version 6 address. And this IP version 6 address is this extremely long address here. I've got an IP version 6 address and then a temporary IP version 6 address. As I understand, that temporary one can be assigned to actually particular applications. I've got both IP version 6 networking available and IP version 4, so the dual stack approach. The other way to get IP version 6 to work, if you've got routers that don't understand IP version 6, only understand IP version 4, it is possible to actually route IP version 6 through an IP version 4 network using a technique known as encapsulation, where you actually embed the IP version 6 packets in IP version 4. So these are all expected to be temporary solutions as we're in the process of transitioning to IP version 6. Okay, so IP version 6 has expanded addressing capabilities, a simplified header, improved support for options and flow labeling, and then also support for authentication and encryption built right into the IP layer. Okay, that's it for this lecture. That actually concludes chapter 10. I believe we're supposed to have a test over the material since the last exam. So I'll talk about our upcoming exam during our Zoom meeting on Wednesday at 2 o'clock, I guess, is when we meet. So I encourage you to attend that meeting. I will put up everything that we cover there in the meeting, all the information about the upcoming exam on the website. Okay, but that's it for today's lecture.